Okay, so point of this quiz, guys, was to show you what it'll be like on your unit exam when you have several different kinds of problems that deal with energy, and that you need to be able to tell them apart, because were both of these actually law of conservation of energy questions? No. The first one's what kind of a question? It's a work energy theorem question. Okay, so it involves a change in energy, right? It's lifted from a height of 10 meters above the ground to 35 meters above the ground. How much work is done? What's the key word there? Work. Yeah, remember we said one of the ways you can tell them apart is to look for trigger words, okay? Like the word work, or if they talk about a force, or they give you a force, okay? Things like that, so that we can tell the questions apart, okay? And know what way to go about solving them. All right. So for question number 1, okay, first off, give them a mark for their givens. We were told the initial height was 10 meters, the final height was 35 meters, and the mass was 200 kilograms. Okay, because we recognize that potential energy is being changed in this question, you can get a mark for identifying it as a work energy theorem question. Okay, and if they wrote work as a change in potential energy, so they got EP there, that's also fine. Okay, maybe they went straight to this step here. If they did and didn't show this, that's fine too. Okay, either way. Okay, next mark for showing that work is m times g times h final minus m times g times h initial. Okay, for that one. Okay, so make sure they show that one. And then plugging in the numbers. So we got 200 kilograms, okay, times 9.81 times 35 minus 200 times 9.81 times 10. So we'll mark for that step. And then our final answer, 49,050 joules worth of work is being done. All right, so that one is out of 5. Questions on that one? Okay. All right, number 2, okay, with the bobsled, okay, bobsled, roller coaster, okay, whatever. There's no force other than gravity working here, so the amount of mechanical energy at the beginning is the same as the mechanical energy at the end. All right, so if they got something that looks like givens, okay, maybe they drew a picture, okay, it showed initial height, final height, whatever, okay, they can have that mark there for givens. Now, the reason I sometimes like to draw a picture for these questions for givens is to help me figure out what kinds of energy the object has at both places. Okay, in this case, it starts 45 meters off the ground, already moving at 12 meters per second, right? If you've ever watched the bobsled, okay, they push the sled, okay, at the beginning in order to get it moving, and then they hop in, right? So it had an initial speed and an initial height, so it has both kinds of energy at the beginning. It's still 13 meters above the bottom of the track at the end, so it still has some potential energy at the end, and we're looking for its final speed, which would imply it has some, okay, and so it's got some kinetic energy at the end as well. Okay, a mark for EI equals EF, or maybe they went straight to this step. Okay, either one of those, as long as they've got one of those, they can have that mark. Okay, then they need to manipulate. What I'm looking for is VF, and it's part of this term right here, so I need to subtract EP final over to the other side. Okay, so you can give them a mark for that. If they did that after they had their stuff plugged in, that's fine. Still give them the mark. Okay. So what we should end up with is, as our next step, m times g times hi, okay, plus 1/2 mvi squared minus mghf equals 1/2 mvf squared. Now, if they canceled the m's, great. If they didn't, I don't know what they were going to do because I didn't give you a mass. So hopefully they canceled it, or maybe they just picked a number. I don't know. Okay. Now we got to manipulate for VF, so we divide both sides by 1/2. Okay, so this whole thing goes over a half, and then we square root. Okay, so give them a mark if they've got something like that set up. Okay, mark for plugging in all their numbers. So 9.81 times the initial height of 45, 1/2 times the initial velocity of 12 squared. Okay, minus 9.81 times 13, the final height, divided by 1/2. Okay, and then our final answer should be that they are moving at 27.8 meters per second at that point. Okay, remember that they must have units on there. If they don't have meters per second or they have some other units, it is not right. Questions on number 2? Question? No? Okay, give them a mark out of 11. Okay, let them see it. Put it in the box. Okay, so the problem we're investigating here, guys, is how much of the available potential energy or work that we're going to do, okay, is actually going to be converted to kinetic energy in a mechanical energy conversion. All right, that's what we want to find out here, is how effective is this energy conversion. All right, so our variables, to just kind of outline how this lab is going to work. We talked about it yesterday, but we'll re-outline here. Okay, you need to figure out from my outline what variable is which. Okay, so we are going to pull back the cart and rubber band, right, to a certain distance. Now, as a result of doing that, we will have done work. Okay? Everything else in this lab depends on that. Everything else in this lab depends on the amount of work or the amount of potential energy that we put into the system at the beginning. From there, we want to find out how much of that potential energy and that work gets converted to kinetic energy in the cart. Okay. Now, there's some things we want to make sure we do the same, because we are going to do several trials just so that we can kind of average things out. Some trials work out really well and the cart rolls a little further. Okay. Other times the cart doesn't roll quite as far, it slips a little bit or whatever. Okay. And we want to make sure we have a few trials to average those out. Okay. Even if you're always bringing it back to the same distance, giving it the same amount of energy and all that. Okay. It can still sometimes change a little bit from time to time. Okay, so we are going to do multiple trials, but with the same input energy each time. Everyone follow me there? Okay, so we're deciding what that energy is. Okay, we're determining how much work, how much energy goes into this system. Okay, we're doing it the same way though each time. All right, so some of the things that we're going to control in this lab. Okay, one of the things that we're going to control is how far back we pull it each time. I know that sounds weird, okay, because you were probably thinking that was the manipulated variable, okay? But the manipulated variable is actually something that is related to how far back and how hard you pull, okay? Incidentally, how hard you pull is another thing that's going to be the same every single time, okay? But they affect something else that's the main variable, okay? We want this thing to go as straight as possible. Is it going to go perfectly straight? Probably not, but we want to make it go as straight as possible. If you get any times where the cart obviously drifts a little bit, okay, and ends up way off to the right or left of center, don't use that trial. Okay? Use trials where the cart goes reasonably straight. Okay? We're talking about, let's say, a sector. So if this was the launch point of your cart, let's say the sector shouldn't be, any wider than that. Okay, so let's say about 30 degrees, okay, as a kind of a sector there. Okay, other controlled variables you can kind of think up, okay, but the force and the distance are two big controlled variables. I'm giving you those two, okay. You have to decide what things they affect, okay. That might be the manipulated, it might be the responding variables. Usually things that are in the problem are good indicators of variables. Okay, for our hypothesis. Okay, in our hypothesis we're supposed to talk about an answer to this problem. So in the if part, we should probably talk about maybe work energy theorem. Okay, or maybe we should talk about law of conservation of energy. There's a couple of ways to go about this one. Okay, but we should probably in the hypothesis if part talk about what the perfect physical world would say. Okay? What would happen in the perfect physical world in kind of a situation like this? The and part as always describes what we're doing. Okay? We're converting one kind of energy to another with this setup. Okay, and the then part should say essentially what will happen with how will the energies compare. Okay, so talk about the law of conservation of energy, maybe say what it is, okay, in the if part, talk about the experiment, and then tell me as a result of that what should be the relationship between your energy at, your potential energy and your kinetic energy. Okay? Now, there's a lot of things you need to record in this lab because we have to do some calculating in order to get our different energies. Okay? So one of the things we have to record is the potential energy. And we've talked about that we get that, okay? The potential energy we get using, okay, the force applied, okay, and the distance that the force acts over. The mass of the cart's not really as important for that part, okay, because the potential energy is related to the elastic band, okay, and we know that because we've done the work lab already, right, where we pulled back that rubber band and figured out how much work was done. Okay. For the kinetic energy, okay, we'll need things like possibly the mass of the cart. I mean, we're going to record that, okay, but most importantly, we need the distance traveled by the cart after it leaves the rubber band, okay, the final velocity being 0, right, and the time that it rolls for. And that is probably the variable that is the toughest to get accurately because it's reaction time dependent. Okay? So there's going to have to be some communication between you and your group members when you're releasing the cart. Okay? So it's going to have to be like, 3, 2, 1, and then the person can start their stopwatch on their phone real quick. Okay? When the cart is released. Everybody with me there? Stopping it on time, that's easy because the cart kind of rolls slowly to a stop, and that part will be easy. But actually getting the start coordinated is probably the most difficult part. Okay? So we'll be recording distance traveled by the cart and the time it takes to slow down. Okay, values we're going to need to calculate. We're going to be using the distance traveled by the cart and the time of the travel and the final velocity of 0 to calculate the acceleration. Okay, to do that, we're going to be using this formula right here. Right, it's already manipulated for you. Okay, you're never going to be asked to use that formula on a test, okay, or on a quiz or anything like that. We just need it for today. It's actually a Physics 20 formula, okay, but it's already been manipulated for you. Okay, so acceleration will be calculated by multiplying how far the cart travels by 2 and dividing by the squared time. Okay, so let's say your cart rolls for 3 seconds and it travels 5 meters. Okay, so you're going to go 2 times 5 divided by 3 squared. Okay, so 10 divided by 9, essentially. Everybody with me there? It's not a hard calculation, but it is something you're going to have to calculate. All right. We're also going to have to calculate the kinetic energy of the cart. And we talked about this yesterday, okay, that we were going to be doing that by calculating the work the kinetic energy would do against friction. Okay, so we're going to take the mass of the cart multiplied by the acceleration of the cart, which we're calculating here, okay, multiplied by the distance the cart travels. Okay, mass times acceleration is force, multiplied by distance is work. Everyone follow me there? Okay, so we're using how much energy was lost to friction to represent the initial kinetic energy of the cart, because that's where that energy is going. All right, everyone follow me there? Yes? All right, and like we said here, potential energy, okay, we're going to calculate by going force times distance using the readings you took in the loading phase. The loading phase is when you pulled back the rubber bands, okay, to the certain distance. Now, there is going to be one little thing with that. You're going to pull back the rubber band with the spring scale the same as you did in the work lab. Okay, I would recommend you probably don't pull it back more than about 10 or 12 centimeters. The further back you pull it, the more likely it is the rubber band just pops the cart and flips it over. Okay, actually the less energy you have, the more likely the cart is to actually roll effectively. Okay, the more energy you put in, the more likely it is to just get flipped, shot, and dragged or whatever. Okay, so we found that in general, if you use a lesser distance pulled back, you generally get better results. Okay, so pull it back first with the spring scale to whatever distance you decide on. Okay, record both of those numbers. Now you can put the spring scale away. Okay, you're not going to need it again because you can't have both the cart and the spring scale attached to the rubber band at the same time. Because when you release the rubber band, both of them will go flying. And that would be bad. Okay, because the scales will get damaged and someone will probably lose an eye. Okay, so we don't want that to happen. Okay, so the first time, just pull it back to that distance, record the force, okay, record the distance, and then put the spring scale away. You're done with it. Okay, after that, you just put the cart in, okay, and pull the cart back in the rubber band, okay, to the specified distance. Now, the technique for that, okay, is that you want to try and get, okay, the rubber band, okay, on kind of these back, that back kind of rounded area there. All right, and then pull it back in the rubber band and fire it out. Okay, making sense? Right. Now, again, you want to make sure that your rubber band is pretty low, okay, so that it sits kind of in the lowest part. If it's too high, you can see how it catches on the wheels there. Okay, we want to try and avoid that. The lower it is, the better it tends to work. Okay, so the procedure we talked about yesterday, attach the rubber band to the two legs of the desk as shown. Okay, make sure you got enough room in there for the cart. Use the spring scale, draw it back, record the force, place the Hall's carriage on the rubber band, pull the rubber band back to the same distance with the cart in it. Okay, have the timer cue the person, release the system and start timing, stop timing when the cart stops. Okay, measure and record how far the cart traveled from the legs of the desk, because the legs of the desk is where it will exit the rubber band. All right. Then you're going to do 3 more trials. So you're going to have 4 trials, okay, in this lab. Make sure you get 4 ones where, again, it travels in that kind of 30-degree sector. Okay, and then you're going to create a chart. Okay, and the chart is probably going to look something like this. Now, I've just got fake numbers in here. This is like old data from another time. Okay, and then you can fill in these as you calculate them after. Okay, so the things you're going to need to have recorded, okay, will be the force you used. All right, so that's right down in here. Okay, and then the distance that you pulled back the rubber band. All right, now, you don't have to use the same numbers I did. Okay, you can use whatever you want. Just remember, the further back you pull that rubber band, the harder it's going to be to shoot your car accurately. Okay, and then for kinetic energy, you're going m times a times d. Okay, so you'll have your 4 trials, okay, and then calculate your acceleration for those, and then you can calculate your EP and EK. You're actually just going to average those. It says that in the analysis, which we'll talk about once you have your data. All right. Questions? I don't want to load you with too much right now, so I'm not talking about the analysis yet. Okay. Everyone knows what they got to record? Force, distance on the rubber band, time and distance for the cart. Okay. So essentially, right now, you need to record 4 things. Okay. How many trials are you doing? 4. Okay. You need to arrange it so that you're shooting your cart essentially up one of the aisles. We can probably have a group here at the front of the room and another group at the back of the room. All right. So there's probably only room for maybe about 5 or 6 groups to work effectively. Okay. But we can all stay in here and get that done. Okay. All right. Okay. So a couple of things here, guys, when it starts talking about the analysis. Okay, it says calculate the work done by pulling back the rubber band, show your work, this will be your potential energy. So show your work, okay, somewhere, either take a picture of it and insert it in here, or just punch it in, okay, typing it in, and then put that number in the chart, okay. It's force times distance, it's not difficult, just make sure you use the right distance, because there's been a few questions this morning about which distance is which, okay. Which distance do I use to calculate potential energy? No. The one to calculate the potential energy is the one for the rubber band. Okay? The rubber band is where the potential energy is, so the distance you pulled back the rubber band is the one you use for this calculation. Okay? For number 2, calculate the acceleration of your cart using your average distance and time. This distance is the one your cart traveled. All right? Because there are 2 distances. When you're calculating acceleration, that has to do with the travel. So it's the distance traveled by the cart this time. Okay? And the time. And remember that okay, that the acceleration formula is 2d over t squared. Okay, that's the one. It's earlier on in the sheet there, but it's there. Okay, you're going to do that for each trial. Okay, and then you'll do an average of it according to the chart. Okay, calculate the kinetic energy of each chart, right? Or sorry, of each cart, and put it in the chart. And we said we were doing that by saying that work against friction was mass times acceleration times distance, and that was going to equal EK. Right? So make sure that you're using which distance here. The distance it went, because that's the distance over which friction stopped it. Okay, so that distance is the bigger one, the distance the cart traveled. All right, then outline again. So you need to explain to me a little bit, kind of in your own words for number 4, what we're doing math-wise here. Okay, and lastly, did the potential energy of the system equal the system's kinetic energy? Why or why not? Guys, that's got to be a reasonably long answer, not like number 2 was in the work lab for most of us. Okay, I want some explanation there. What are some other places the energy went, other forms of energy it became, things like that. Okay, and then same as always, conclusion and evaluation. Okay, you guys know what to do there. Are there any questions on the calculations and analysis you need to do? All right, one last thing as a quick review here of the variables. Okay, there are a lot of variables in this lab, right? But when we're talking about the manipulated and the responding, okay, think about what this lab is comparing. It is not, those two variables are really not anything small that you measured, okay? Those two variables are the main things in this lab. You need to explain why. All right? Okay, the due date for this is June the 4th. That's the day after the unit exam. Okay, I will also pass out your unit exam review packages here in a minute.